Thank you very much. Thanks for the invitation and the opportunity to speak here. So I was just told that the title of my talk changed a bit. In fact, the content didn't change. I just forgot that what I wrote in the program. So this talk is about machine learning on the symmetric group, and I will explain what a symmetric group is, but basically it's when you have data which are rankings. So I think the original title was learning from rankings or permutations, and this one is the same. So obviously this talk is a bit more on the machine learning side and on the imaging side of the workshop. And the obvious reason is that I myself do not do much or any research on imaging. But I decided to talk about that because there may be some links to imaging. I will give a few examples of why this could be relevant. And obviously all the images I will show will be very, very naive applications, very poor performance, etc. But my goal is just to share with you some techniques maybe that potentially could be useful for applications on images. All right, so the machine learning side, I will just focus on the most simple and obvious machine learning problems. You have points, typically binary classifications. Your goal is to train a classifier that would discriminate the points. And if you're in a good space, lines are enough or linear separators are enough. So the idea would be once you have mapped your data to some space where the classification problem becomes easy, you can just do a linear model to separate points and then do predictions. Okay, that's what we want to solve. Now you see that in this picture you have black and white dots, which are your data. And depending on applications, you need to decide what are your data. This could be images if you want to do object recognition in images, for example. This could be genomes if you want to do precision medicine. And here I will just focus on the mathematical part of it, and I will discuss how you can do that when your data are not images or genomes, but when there are permutations. So if you're not familiar with the field, this may be the most important slide because it explains what I mean by permutation and by rankings. So a permutation basically is just is the standard vocabulary in mathematics, right? There is nothing new here. Permutation is just a bijection, so a mapping one-to-one between the integers from 1 to n, where n is fixed, to itself. Okay? For example, in this picture, which looks nice, this picture is just a way to visualize all permutations of 4 items. So if you take 4 items, meaning you take n equals 4, and you consider how many ways there are to map the integers 1 to 4 to themselves. In fact, you will count there are 24 ways to do that, which are depicted here as the, in small letters. For example, the bottom one, which I write 1, 2, 3, 4, is just a convention to say that sigma of 1 is 1, sigma of 2 is 2, sigma of 3 is 3, and sigma of 4 is 4. I just write the images of 1, 2, 3, 4, and I get one of them. Now, all the edges here, for example, 2, 3, 1, 4 is another permutation. And if you list all of them, you get a set called the symmetric group. We call that a group because it is a group in the mathematical sense, because when you have 2 permutations, you can compose them, right? Composition creates a group operation. And just for information, in this picture, you see that we organize them in a graph. The way we did that is just, for example, we added a blue edge between any 2 permutations, when you can go from one of the other by just permuting the first 2 indices, right? And then you put a red edge for some other reasons, and you get a picture called the Cayley graph of the group. Okay, so this works for 4 items. Now, if you have, let's say, not 4, but 1,000 items, which will be typically what we'll do, then you can imagine the same picture with factorial 1,000 vertices. You can connect them if you want, but you see that the symmetric group can be large. And so what I would like to discuss is, suppose that your data in this picture, each dot, is not a vector in the 2D space, is not a point, but is one of the permutations. It could happen, for example, if you collect data which are permutations, which have a label, like 2 classes, and you want to discriminate permutations, meaning you want to separate the space of all permutations into 2 parts, the ones that you would predict as positive, the other ones as negative. All right, so why would we want to do that? Besides the interesting aspect of it, I think there are quite a few applications, and this will be my take on images. I'm sorry if it's a bit naive. But before images, let's look at some data that are already permutations. In fact, there are many applications where you can collect data and you want to do machine learning on data, and the data themselves are can be naturally seen as permutations. Right? So the first one is supposed to summarize. Typically, if you collect data which are preferences or rankings, for example, you ask people what drink they prefer among 5 drinks, then everybody will rank the 5 drinks. And you can describe one person by its preferences, its ranking. And then if you collect lots of such data, maybe you want to predict something else from the preferences. So you see it's a case where the input data would be a ranking, or maybe a partial ranking. There are many extensions of that. And you may have labels and want to fit a model to predict something from the preferences. That's one case. Now, the reason why I got interested is more related to another case, which is when you have data which look like numbers, like vectors. For example, you can take an image. An image is a vector in the space, of dimension, the number of pixels. So each pixel would have some intensity. You get an image. But as far as I heard and as far as I know, sometimes, if you look at Photoshop, for example, when you have an image like this, you see it's not very good quality. And one way to enhance the quality is just to change the histogram of intensities. Right? So imagine you take this image, you see it's grayish. So if you plot what intensities are used in the image, they are concentrated on a small window, probably of gray value. And one way to enhance the contrast, sometimes called histogram equalization, is just to say, let's transform the histogram of values into something else. And on the right picture, for example, when you do histogram equalization, as far as I know, you just impose that the histogram of values is flat, uniform, between 0 and 1, for example. Right, so what's the link with permutation here? Well, if you think of it, what you did to go from the left to the right is you took all the pixels, you ranked them from the most white to the most white, so from the lowest intensity to the largest intensity. You keep just the information of the ranking, and then you assign new values to each pixel so that the histogram of values changes, in this case, to be uniform. Okay, but this means that from left to right, the information about the histogram of intensities has disappeared. This is not something you have kept. And to go to the right, you just have kept the information about the relative ordering of the pixels. Right, so this is something you can see as a permutation. It means that when you start doing this operation and then doing anything with the right image, it means that you have started by mapping the image to this symmetric group, where n in this case is not 4, but it's the number of pixels, a few millions. And then each image becomes one object here. To go to the right picture, you have done some further operation, going from the permutation to assignment of values, and then doing something else. But okay, so here, the motivation is that in some cases, if you believe that the values in a vector are not important, but the relative ordering of the feature is important, naturally, you're interested to study what happens when your data are permutations. All right, just to give a last example, and this is what motivated more my own research, because as I said, I don't work on images, but on other topics. When you work with experimental data, let's say in biology, when you do sequencing or transcriptomics, there are many technologies that measure lots of data about samples. And when you have experimental data, a bit similar to images, you can have various technical artifacts, batch effects, when you measure something in a cell, depending on the pressure in the air, the temperature, day of the week, etc., you may have values which are not very reliable. And so depending on what you measure, there are cases where we believe that more important than the values are the relative values between things you measure. Like you measure expression of 2 genes in a cell. Maybe it's hard to quantify exactly what we mean by expression, but it's easier to say that in one sample, the first gene is more expressed than the other one, and maybe in some other tuple, it's reversed. Right? So in these applications, and typically in bioinformatics, for example, there is a normalization quite similar to this one that is operated on many, many data, which is called quantile normalization. It's different word, but the same thing. It's when you start from a bunch of data. Here, imagine that each box plot will correspond to one sample, like one image. And you see that when you have many samples, they differ a lot by the histogram of values they have. And so quantile normalization is about saying that when you have different samples like that, maybe it's relevant to normalize them so that after normalization, they have the same histogram of values, but they are not all the same samples, because here I just showed the values that you measure. What's different is the relative ordering of the features, exactly like this. Okay? And so this transformation is, people don't even say they do it, they just do it in bioinformatics, because if you don't do it, you obviously get, you cannot do anything from the raw data, typically. All right, so after motivating why we may care about permutations, let's see how we can do machine learning on permutations. So of course, there are many, many ways. I will just try to explain what we could do if you want to really do what was in the first picture, meaning having dots and drawing a line between them. A standard approach would be to say, if I have data, which in this case would be permutations, and I want to learn a mapping, a function over the space of permutations, one way to do is to first embed or map the permutations to a continuous vector space, where then we can do linear functions, for example. So it's a notion of embedding or representation, to say that you have some objects and you represent them as vectors, and then once they are vectors, you can do linear models. That's what people do in deep learning for many things, word embedding, text embedding, image embedding, etc. This is all about representing some data as vectors. So the question could be, is there a way, natural way, to represent permutations as vectors so that later we can put them in some linear model? Right, so this is what I will try to keep the notations where sigma would be permutation, and we'll discuss how to create a mapping phi that transforms so the space of permutation is discrete, right? So it's still possible to talk about a mapping phi that transforms any discrete permutation to a vector of dimension p, and then we'll focus on linear models if we want, even though I will not insist on the linear model itself. Just in terms of vocabulary, as soon as you have a transformation to vector space, a mapping to vector space, you can call kernel something which is just the inner product in the feature space. And I will use the word kernel sometimes because it's useful to explain some of the geometry in the feature space. So kernel is just something associated to the mapping phi and defined as the kernel between two permutations is defined as their inner product once you have transformed them into vectors. Question?
Can you explain again why we map R with F? What kind of things are we trying to predict?
So the first one is just to mean that suppose we want to do that. Okay. Here you see, here I draw a line, but in fact the line is a linear function, represents a linear function that in this case would be thresholded to define two classes. But the general setting will be, we have points and we want to define a function, a real valued function. This is what machine learning does in general. And so again, we want to define a real valued function that will be an inner product after embedding our data in some feature space. And so if you have that, you can do regression, classification, PCA, whatever. You can do lots of things. All right, so the question would be, how do you do that? And obviously, it's very easy to imagine any possible phi. You can just say, it could be random phi, or you can say, I map this permutation to this feature. It's possible to imagine many things. So the question is are there some principles that could allow us to decide of some mappings, some embeddings more relevant than others? And so, it's like a bit feature engineering to some extent. How do you define the features or the representation of your data to solve a problem? And so there is no big thing to say except that certainly we want to embed in a space where, for example, our machine learning problem would be easy to solve. I said once your data are well separated, then it's easy to learn. So depending on the application, you may have different thoughts on that. Something that could be a bit problematic or specific for permutations is that, remember, there are many possible permutations. So as soon as you start talking about, and we'll see a few examples, talking about embeddings, very quickly you may end up with embeddings which are NP hard to compute or with exponential time to compute. So maybe in some applications, for example, if you want to work on images where n is in the order of millions, you don't want to have an embedding where the cost of embedding is n to the 6, for example, because it would take just a few hours to embed one image, which is not practical. Right? So these are like two constraints you may think about, and I will add a further one, which is a bit specific, which is important, and which will allow us at least to describe all possible embeddings that fulfill this hypothesis. So the last one is a notion of invariance, and we call that right invariance in this setting. technically, it's just defined by this equation, and I will explain what it means. So we say that a mapping, so here, remember, for each mapping phi, I define some inner product called a kernel. And we say that a mapping or a kernel is right invariant if and only if, when you multiply on the right two permutations, their inner product in the feature space doesn't change. Right? Remember that K is the inner product, so you have two permutations, sigma 1, sigma 2. You have a mapping phi, so you can compute their inner products in the feature space. And what we impose is that if both permutations are multiplied on the right by a fixed permutation, they will change in the feature space, but you would like the angle or the inner product not to change. So why would we impose that, and why right invariance and not left invariance or any invariance? Here the right invariance in this case corresponds to something very specific. It corresponds to a redefinition of what we call the items 1 to n. So let's take the example of the, I'll come back to the image, for example. Here I say we have an image and we transform it into a permutation. Mathematically, permutation is this sigma that says what is sigma of 1, sigma of 2, sigma of 3, etc. Okay? So to define this permutation, I need to give some, I need to impose a first labeling of the pixels. For example, I could label the pixels from 1 to n, from upper left to the bottom right, saying 1, 2, 3, 4, 5, etc. And once you have defined this initial way to label your pixels, then you can talk of a permutation. You can mathematically say, now that this is pixel number 1, I can compute sigma of 1, it's a number. Okay, so then you define the sigma that is dependent on the initial way you define your ordering of pixels. Now suppose someone else comes and says, my way to label the pixels is different. I will start from here. This is 1, 2, 3, 4, 5, 6, etc. Then the same image, you can also compute a permutation sigma that will represent the same image. But the sigma will be different because your initial ordering, your initial labeling of pixels is different. And when you think of what's the link between the permutation of the second person versus the first person, it's just this multiplication on the right. It means that you take the same ordering, but the pi corresponds to the relabeling arbitrary of the pixels. Okay, so when we say we want to be right invariant, it just means that we want to create an embedding such that the geometry in the embedding should not depend on how we initially name our pixels. Okay? Of course, the feature will change, like phi of sigma will not be the same as phi of sigma pi, because we want the space to, to separate the things. But we want globally the full geometry. Imagine you map all the permutations in your continuous space. You want that the geometry does not depend on how we initially call the pixels. And this is the notion of right invariance. Okay, so once we have said that, we will say let's look for mappings, phis, that embed permutations in a right invariant way, and then maybe we can do machine learning that will be, by constructions, invariant to some arbitrary numbering of the pixels in the feature space. So I will now discuss quickly two things we've done with my students. So I will talk the work of Yunlong Zhao and of Morvan and Vert, two very talented former students, who worked on, I will present two of them and then make a bigger picture of the field. So two permutations that, imagine that particularly this is, I will use this picture to suggest this is a permutation. So think of it as just a series of values, but you just say the order. So let's say the green will be number 1, the red will be the last one, and the gradient tells you which order they are. So this would be your sigma. And we will discuss two of them. One I will call the Kendall embedding, the other the SUQUAN embedding. We'll explain what it means, which correspond, you see, to two ways to transform a permutation as vector. So not that here, I plot a matrix. So matrix is a particular vector of size n squared. So this will be two embeddings in n squared dimension that I will discuss. And then we'll see that we can do more than that. All right, so to make the story a bit concrete, even though there are still a few equations, let's look at this embedding. So this embedding is maybe the most natural embedding you can think of when you think of the problem, how to represent a permutation. And I will explain what it means, SUQUAN. But here we take sigma permutation and we say let's represent this permutation, sigma, by a n by n matrix, so n square numbers, a binary matrix, only 0 and 1s, with basically mostly zeros, and there are just 1s at positions that describe which item is in which position. So technically, we say that the ijth coordinate is 1 if and only if sigma of I is equal to j. This thing is the standard one, like it's even called the permutation representation in mathematics, right? If you have permutation, you say, let's look at the permutation representation, or sometimes we call that the permutation matrix. It's just a way to encode the permutation in a square matrix. So why not? I will explain why not or why it could be interesting, but notice that this one is indeed right invariant. I'll leave it to you if you're interested to do the math. Very easy to show that if you multiply on the right two such matrices by a given other, the matrices, then the effect of the pi will disappear in the inner product. Okay, so that's one example of a right invariant representation of your permutation. And potentially, if you have a set of sigmas, then you can compute their matrices. Each image would be such a matrix, so it would be a big matrix. If an image has 1 million pixels, this would be a 1 billion by 1 million matrix. But potentially, you could do a linear model on that. It may be interesting or not, probably not, but this is possible. So let me try to justify why it could be interesting if you impose, in particular, some constraints on the linear model you do, and make the link with quantile normalization or histogram equalization, just to try to explain why this name SUQUAN appears. So the link with quantile normalization is, if I come back to my example of an image that we said we want to visualize it in a better way by enhancing contrast, just by taking the original histogram of intensities and flattening it to uniform, for example. If you write mathematically the operation, what we do is the following. We start from an image x, right, which is a vector of numbers. Then we compute the corresponding permutation by just ranking the pixels. So from the image, we just extract a permutation, which I call sigma of x. And then how do we go from this permutation to this image? You see that this image, what we've done is that we've just assigned to each pixel some predefined value by some target distribution. So for example, if you want the histogram to be uniform, we define a vector f that would take all values in a uniform way between 0 and 1, for example. And then what we want is that if I call psi of x the right image, indexed by f because f would be the target histogram of intensities, then the definition is just that in this vector, the ith coordinate is just the value of our target vector, but indexed by the position that is the rank, to a given pixel, you give the value depending on its rank. So this is formally what you do. And if you think a bit about it, this can be summarized in just a simple matrix multiplication thing, which is that to obtain this image, you just extract the permutation, you compute this matrix representation of the permutation, and you multiply it on the right by your target vector f. Okay, so technically, going from here to here amounts to computing sigma of x, then computing the matrix representation of the permutation, and multiplying on the right by f, which would be the target vector of values, let's say from the lowest to the highest. Okay, so this representation pi appears here naturally when you do this quantile normalization operation. Now, something slightly interesting is, when you do that, I keep saying this is technically a way to enhance contrast, and when you do that, you need to specify what is f. F would be the histogram on the right. It seems to be arbitrary here, right? If you give me a f, for example, uniform, then you get this picture. But I suppose that if you take someone working on computational photography, he may tell you, this is stupid to take uniform, you should take a Gaussian, or you should take a bi-Gaussian, or there are many ways. So the question is there a way to choose what could be a good target histogram, good target quantile of values if you work on images or on gene expression or something else? And I would say that as far as I know, talking to people or reading papers about that, it's not very clear how to fix that. There are heuristics, like some people say you should just collect a bunch of images and average the profiles you see on images to get a fixed one. That would be nice. Others say you should just target the uniform distribution. Others say you should say that. So there seems to be some degree of freedom in how you make your normalization by just choosing the target histogram of values. Now let's see how we could maybe optimize the target value, and this will justify why this embedding is interesting. So here, remember I said when you do machine learning, you first map your data to some continuous space, and then you may want to do a linear model in them. So let's try to write down what it does when we choose this mapping. So for example, when we do a linear model over this image. So doing a linear model means that first you transform your images with this transformation, and then you create a linear model on the corresponding new image. Making a linear model, I don't want to confuse you with the notations, but typically when you make logistic regression, if you do neural network, you would say softmax, last layer, etc. It just amounts to say that you have your data, psi of x, I, which would be the ith image, and you make a linear model, so typically multiply by a vector w. You need to adjust, you need to learn the weights w, maybe with some b, and you have a loss that is average over the example of some loss function that would say, for example, you're in the good class or not. Okay, so this thing is just typically what you would do if you train a linear model over the modified examples, the modified image, after quantile normalization. You would typically solve this optimization problem and find a linear model. Now you see that I said that here, when I write this, it's after normalization of your data by quantile normalization, meaning typically you first fix the target vector f, that would be the values you want your image to have after normalization. Then you normalize your image, and then you fit your linear model. Now, if you have these two steps, you could say maybe instead of fixing f a priori, I could put it in the optimization model, and maybe I can learn the best target histogram so that the machine learning problem is better solved. And because the machine learning is about optimizing something, a slight modification is just to keep the same target, to say I want a good discrimination, but not only, to give one more degree of freedom, which is not only to optimize the linear model once I have mapped my data to the linear space, but also to optimize the representation by letting f be a parameter here. And to say that maybe I can jointly optimize the target quantile and the linear model so that globally I have a representation that is good for my problem. Right? And so this is why we call that SUQUAN. SUQUAN means supervised quantile normalization. Right? It's just a way to say we do quantile normalization, but we also optimize the target distribution so that so for a given target which is solving a machine learning problem. So I don't talk much about, there are terms on the right just because when you learn in high dimensions you need to regularize. But the important message is that it's roughly the same problem, but we just add one variable, which is optimizing jointly over the linear model, WB, and f, which is what the target quantile that you use when you do your normalization. Okay, and here comes the slightly interesting observation, even though quite trivial if you just do a computation. Is that when you do that, so when you say, I make my linear model over the transformed data, and I jointly optimize the linear model, so the line, and the histogram, which is f, if you write down explicitly what you've done, remember that I said that transforming an image x into, doing quantile normalizations amounts to multiplying, to a matrix multiplication. It corresponds to saying, I take x, I compute sigma of x, my permutation, then I do the matrix pi sigma, and I multiply on the right by f. If I just come back, this is just what I said here, right? Explaining that to go from the left to the right, what you do mathematically is pi sigma of x times f. So let's just plug in this formula to get the full picture of what we do when we normalize and make a linear model, right? We normalize and make a linear model. And now if you say that you optimize both W and F, you see that suddenly they just pop up as two vectors in this thing. In fact, you can put them in the same side by just some manipulations of matrices, standard ones. and this is the manipulation. This inner product is just the inner product, the matrix inner product between your matrix pi, so this binary matrix that represents an object, and the new matrix, which is FW transpose. Right? And suddenly there is like a symmetry that appears between F and W, even though when I explained it, they look a bit different. F was supposed to be just the target histogram. W was the linear model after normalization. But if you just combine them and see what you really do when you do normalization followed by linear model, you just multiply this matrix pi, so the one with binary entries, by a new matrix FW transpose. And your question is how to optimize F and W so that this is a good linear model. Right, so this means that you can reinterpret the normalization followed by linear model with optimization of the normalization just as a linear model where each image, so I talk of images, but each sample xi is represented by the matrix pi sigma. Right? So this is my embedding, where I say you have sigma, you represent it as a matrix. Here it is. And you make just a linear product. So this is a linear model over matrices. And the matrix of weights now is a bit special because in this case, it's just a rank 1 matrix. So it's not any linear model. It's just among all linear models defined by matrices, you focus on a subset of them, where you don't need n square parameters, but just 2n parameters. This is your target matrix. And if you optimize this, you get exactly what you do when you do quantile normalization by joint optimization of the quantile and the linear model. Right, so, okay, this is, I would say this is an observation that links two things together, but it also means that, this naive embedding, this naive way to represent a permutation as a matrix can be used, and in particular, if you constrain the rank of your linear model, you can interpret it as supervised quantile normalization followed by linear model. All right, so I will not spend too much time on, I don't have very exciting results to show, but just illustrate what you can do, and maybe I'll just focus on that. For example, if you take images, and here we just took images from CIFAR 10, and where you have images, small images representing objects, and you want to discriminate objects. For example, this is a horse and a plane. If you train a model to separate them, here, for the sake of easiness and interpretability, we just do linear models over the pixels. Sorry, there is no feature, there is no convolution, whatever. Just straight linear model, but we say, can you discriminate this from this by doing a linear model over pixels, using this representation, right? So saying we first extract the permutation, and then we optimize this rank 1 matrix that would correspond, that you can reinterpret as a linear model after normalization of your data. And so what's interesting, and I don't have time to go to the details, but depending on the constraint you put on your target histogram, you can get different behaviors. And typically, when you make this histogram, it means that the values the function take, so the values of f, have to be increasing because you want them to represent the successive values. And if you just constrain, if you, in optimization, if you just say optimize this under the constraint that f is a non-decreasing vector, like you want values that go from low to high, then you can convince yourself that this would lead to a piecewise constant vector, just because the constraint is, fi plus 1 has to be larger or equal than fi. So when you optimize this, you will typically hit the constraints, and f will be typically piecewise constant. And so on the right, this is an example of f that was learned automatically when we ask the model to discriminate between the two types of images, horses versus planes. So this one here is the f. So what does it mean? It means that automatically the method decided that when you have the input images, the best way, according to this optimization problem, the best way to normalize the image is just to take, in this case, 3 or 4 values and to rank the pixels, then to assign 0 to the I don't know, 20% lowest pixels, then a middle value to the next pixels, and then completely 1, which would be white, to all of the pixels. So in fact, this corresponds to quantization of the values. But the quantization has been optimized so that then it becomes easier to discriminate. So it means that what has been learned is from the original images to transform them into this kind of images, and then it was considered that this representation turns out to be better than the original one when you make a linear model over the images. Right, so maybe there are ideas here that could be made more rigorous and applied to some domains where by doing this thing you also lead to models where you get for free some optimized quantization, quantization being optimized for a given task. Right, this is the idea here is that once you want to discriminate these, then maybe this is the best quantization. And if you have some other problems, maybe there is some other best quantization. All right, so that was one embedding, and I said I have a second one, and then a generalization, which will be a bit hard to fully explain in the last 5 minutes or so. So let me just say that we saw that one embedding is to say I have sigma, and I can represent it as this matrix, the permutation matrix, and this, if I do a linear model of rank 1 on this matrix, can be interpreted as quantile normalization followed by linear model. Now, there are many limitations to this embedding, in particular when you make just a linear model here. You see that the features, when you have a new image or new permutation and you do that, then a linear model on this image just sums the, you will have some matrix of weights that have been learned, and you do multiplication between this matrix of weight and this matrix here. So you see that the only information that is used is when there is a 1 or 0 in a position, meaning when you know that this pixel is at this position. This will have a weight. And you see that it's a bit limited in terms of expressiveness when you just make a linear model of such features. So something else that we worked on with Yulong, Zhao, is another embedding, which I again represent as a picture. So you see it's similar way. You start from sigma, but this time you create this matrix. What is this matrix? You see there are more, it's still a binary matrix. Still one way to represent a permutation as a vector in the space of matrices. And the definition is, again, very trivial. You put 1 at position ij, if and only if, after permutation, so sigma of I is smaller than sigma of j. Right? So instantly you see that you get more or less half 1s and half 0s up to the diagonal. So the matrix is bigger. It's related to the first one, like you can, if I have time, I will write the equation. You can go from one to the other by some operation, but it's different, meaning that if you do a linear model here, imagine you learn a linear model, meaning you learn weights for each feature here. You see that the features which you use are not only is sigma I equals to j, but here it would be is sigma I smaller than sigma j, and you would have a weight on that. So in some applications, like I said in my biological applications, this could be more relevant because here you would use things like you have a weight if this gene is more expressed than this gene, or this gene is more expressed than this gene. This seems to make more sense than saying I'm interested in whether this gene is ranked at position 753. This would be too specific. Okay, so there are many things that can be said about this particular embedding. In particular, when you think, when you have your permutations and you map them to this space, it's possible to study a bit the geometry in this space. For example, what is the distance between two permutations? What is the inner product? And there are many links with standard notions in statistics. For example, the inner product between two permutations in this space is the number of concordant pairs, meaning you have two permutations and you count how many pairs ij are in the same order in two permutations. This is exactly the inner product. And this is, if I directly jump here, this is typically what's called Kendall correlation, up to division by the total number. So Kendall correlation is a correlation measure between vectors, which is defined as the percentage of pairs between two vectors which are in the same order. So here we get this Kendall correlation as inner product in the feature space. And when you take two permutations, you look at their distance in the feature space, how far they are, you take the Euclidean distance, you get the number of discordant pairs, which is also something that is a common thing that we use to define distances between permutations. And so this leads to the fact that you can create a family of other kernels. All right, so I skip a bit, details about the fact that even though this is a big, there is some interesting computational effects here, which is that if you do this embedding, you see you move from the space of permutations to the space of n by n matrices, which may be costly if you make linear models. But even though you have n squared dimensions in this space, all computations can be done in n log n using sort kind of algorithms. So you can work implicitly in the space and have computational advantages, and you can work in very, very large, I mean, n can be large, and you still work in n log n if you don't have too many examples to study. Okay, so given the time, I will I don't have much details, but just mention that you can extend this in two directions. So, I said that here we created this matrix embedding, and we observed that in the feature space, magically or not, the inner product is something that people use people working on permutations use every day, the Kendall correlation. So an extension that could be interesting is, and this is something that people using permutations work on, is can you make a weighted Kendall correlation? Because typically when you compare two big vectors, the Kendall correlation measures globally if the pairs are in the same order, but sometimes we just want, for example, to focus on the top of the list, because the top of the list is more informative than the bottom of the list. So there's a question, can we make a weighted Kendall correlation, and could this weighted correlation correspond to some inner product in some feature space, so that we can use this weighted correlation to train model in machine learning, right? And in fact, there are many attempts in the literature to extend the notion of Kendall correlation to a weighted correlation by saying we put weights on the items or the rank, but none of the existing ones is an inner product for different reasons, either because they are not symmetric or not right invariant, so we want something which is right invariant. So none of the existing things corresponds to some embedding which is right invariant and so can be used in our setting. And so we worked a bit on that, and when you ask the question, it's quite easy to propose a solution to the things. So it's possible to define a weighted Kendall correlation with some equations, which can be computed efficiently. And I'm sorry, I go a bit fast now, because otherwise the chairman will not be happy. But just the thing I want to show quickly is that when you move to this extension from Kendall to weighted Kendall, there's a question of who decides of the weights. Like I said, maybe we want to weight more heavily the top of the list than the bottom of the list. So this translates in our framework as defining some weights that depends on the rank. And then once you define the weights, you can have this weighted Kendall that corresponds to an embedding. And the question, if you ask the question, how do we set the weights? It turns out that it's possible, just like in the first part for SUQUAN, to say that the weights can be left as free variables, and you can put the optimization of the weights in your machine learning problem, so that you have an embedding that depends on the weights of the weighted Kendall, and then you optimize the weights so that your linear model fits well. And surprisingly, if you do some math, then you can show that optimizing both the weights and the linear model in this embedding looks, looks kind of similar to the SUQUAN case, in the sense that it also corresponds to writing in a bigger space. Now we worked on the n squared by n squared, n squared, so n to the 4 by n to the 4 matrices. It's a tensor. But forgetting about the size of it, what we see is that some inner product corresponds to, you have a permutation, and now instead of mapping it to this matrix pi, you create mathematically this tensor product pi by itself. So this is big in dimension. But the linear model is just a linear model in this space here, where the parameters of your model include the weights of the Kendall kernel and the weight of your linear model. Right? So it's a bit the same story as the SUQUAN, except that here I talk of Kendall kernel. But again, we can jointly optimize the weights that define the representation and the model that does the discrimination. And it's a new embedding, which is just, instead of pi sigma, we need to represent, in this case, a sigma by pi sigma tensor product itself. All right, so that's pretty much what I wanted to say. And I would just mention, this is technical, and just if you're interested, we can talk at the coffee break about that. I insisted on two mappings. So there was the SUQUAN, which says maybe I can just jump here. SUQUAN says, let's represent it this way, and there's a link with quantile normalization and supervised quantile normalization. Now, then I talked of Kendall, and when we extend the Kendall kernel to the weighted Kendall with optimization of the weights, it's another representation that is quite natural, which looks a bit the same as the SUQUAN. Maybe I can write it here. Well, pi sigma squared itself, or pi sigma alone. And in fact, it's possible to describe all possible right invariant embedding, and this is too long for today. But there is a nice characterization in terms of something called the Borner theorem, for those of you who've taken my class on kernel methods. It's possible to do Fourier transform on a group and describe all functions which are valid inner product, which are right invariant. They are defined as the ones which are positive in the Fourier domain of the symmetric group. And so these are just two examples of a bigger family that potentially could be studied more systematically. So I thank you for your time. There are many open questions, and I'm happy to answer any of your questions if you have. Thank you.
Is there some questions right now?
I had a question about the first part of the talk. So in the setting you presented, you have this matrix M, which has a rank 1 structure that naturally arises. And I was wondering whether, if you assume that this matrix M has a rank higher than 1, you can still get a nice interpretation of what's going on.
Oh yeah, sure, yeah. So this is obviously a good idea, and we did not investigate much about that, but to have the interpretation as supervised quantile, you need rank 1 and increasing f. And then you have this interpretation. But once you write the model, obviously you may want to say first f maybe doesn't need to be increasing, so it's not a quantile anymore, but it's just a transform of the values. And second, as you say, why just do rank 1? If we do rank 2, we can collect more, or 3. And so typically, I guess having some constraint on M is important. Could be Frobenius norm or rank. But yeah, so doing a low rank optimization could make sense here. It's just a parametric model in this case.
So let's take the speaker again to keep on time.
Thank you.